Hi, I'm Yeseung from Robust Intelligence and Robotics Lab at Korea Advanced Institute of Science and Technology. In this video, I'd like to present the paper titled with GraphDistNet, a graph-based collision distance estimator for gradient-based trajectory optimization. First, let me start with trajectory optimization. Suppose we want to make a robotic manipulator move from a start pose to a goal pose. To do that, we need a sequence of poses called trajectory to avoid obstacles while moving. But as seen in this left figure, a trajectory may overlap with the obstacle that causes a collision between them. To figure it out, we need to optimize the trajectory, minimizing collision cost while achieving the task objectives, which include path smoothness. The optimization process often requires collision gradients to efficiently update the trajectory into a collision-free region. The right figure shows a collision distance map where each color represents the collision distance at each joint configuration. The differential value at each point of this map gives a collision gradient. With the collision gradient, the optimization process gradually updates the initial trajectory, having collision-free poses. In this scheme, we aim to efficiently and precisely estimate a collision distance as well as its gradient for trajectory optimization. Previous approaches in this collision distance estimation field have two major challenges. One is that traditional geometric algorithms generally take a long time to compute a large number of problems. Second, other data-driven algorithms are not easily scalable to more complex or unforeseen setups due to restricted representations. To overcome the challenges, we propose a new data-driven collision estimator, GraphDistNet. GraphDistNet precisely estimates the collision distance by taking the geometric attribute information into the neural network-based estimator. GraphDistNet takes the graph of the robot and obstacles as input and returns the estimated collision distance as output. Also, GraphDistNet has the capability of easily calculating the collision gradient using the backpropagation algorithm built in the neural network framework. GraphDistNet computes a large number of queries fast due to the parallelism of GPU and show more scalability since it is possible to calculate distances in shape-changing environments using geometric features. GraphDistNet has four main procedures. First, in the graph connection step, GraphDistNet connects the nodes between the graph of the robot and the obstacle. Second, in the convolution step, GraphDistNet aggregates geometric information and updates the nodes by the message passing convolution. Third, in the attention-based sampling step, the attention mechanism scores every node and samples new nodes based on the score for next graph connection. Finally, in the readout step, the attention-weighted features collected from every layer are collapsed into one scalar value used to estimate collision distance. These are the evaluation environments. We tested with 2 DOF and 7 DOF robots with fixed or varying obstacles in two-dimensional environments. Environment A, B, C, and D use box-shaped obstacles, while environment E uses randomly generated non-convex obstacles called alpha shapes. Using these environments, we compared one geometric method, FGL, and two state-of-the-art data-driven methods, ClearanceNet, DIFCO, with our method, GraphDistNet. These bar charts show the evaluation results. The left chart shows the elapsed time for computing 5,000 queries. Although our method does not always have the shortest time, The results generally show low and consistent computation time for obstacle-varying environments. The other methods are either not having consistent computation time or having low accuracy in complex environments. The right charts show mean average error, MAE, and area under the ROC curve, AUC, associated with the ground truth data. Our method always shows superior accuracy to other methods. We demonstrated our algorithms with trajectory optimization throughout the real-world experiment using our manipulator robot, only using 3 DOF. The task is to fetch the wood stick, avoiding any collision with the environment, including the storage blocks. Compared with DIFCO, other state-of-the-art data-driven method, both methods showed collision-free leaching paths into the storage. But when the robot leaves the storage after grasping, the baseline method DIFCO could not make a precise collision-free path. In contrast, our GraphDistNet could successfully make one, including object geometries. This is the end of my presentation. Thank you for listening.